Hello, hello. So the next question that we have is lowest common ancestor in a binary tree. This is a question from Geek for Geeks and it is a medium tag question. It has an accuracy of 39.75% with submissions of 100k plus. So this question is about finding a common ancestor in a binary tree. Uh, Go ahead, read the problem statement and try to comprehend how one can approach the problem. And then we can actually start discussing what is being asked and what is to be done. Have a look at the examples as well. So let's have a clear understanding of what is being asked of us. We are given two nodes n1 and n2. And in this example, let's take them as the node with highlighted in yellow, that is node 8 as node with value 8 as n1 and node with value 36 as n2. So we have been given a binary tree and two nodes n1 and n2, and we are supposed to find the common ancestor, and not just the common ancestor but the lowest, that is the most recent common ancestor. So if I start with 36, 14 is the father of 36, parent, not father, parent, we call it parent child relationship. So 14 is the parent and 36 is the child. So this is the child and here it is the parent, and parent is nothing but an ancestor. So 14 is an ancestor of 36, and to be precise it is a parent. And then 2 is the parent of 14 and therefore is the ancestor of 36 as well. So 2 is also the ancestor of 36. 7 is the ancestor, and yes, of course, root is the ancestor of every single node on the tree except itself. So we have the ancestors of 36 listed, and then for 8, 7 is the ancestor of 8, and to be more precise, it is the parent of 8. And 1 is, of course, the ancestor of 8 as well because it is the parent of 7. Now, in this, the lowest common ancestor is over here, that is 7. So I'll just remove the double ancestors, but you get the idea that these ancestors are common and this one is the lowest common ancestor. And now, how are we supposed to do that? The problem that we have in achieving this solution, or in achieving the or identifying the lowest common ancestor, is that in tree we traverse downwards, not upwards. And you saw that in solving this problem, what we did is we traveled upwards. What we did was we traveled upwards, and when we reached here from both the nodes, the common meeting point, the first time the path crossed, we stopped and called it the lowest common ancestor. But the problem is, as I mentioned, in tree we cannot go from child to parent. We can go from parent to child, however. So if I were to go down from parent to child, um, how do I know if 7 is the lowest common ancestor or is the ancestor at all of 8 and 36? So maybe there is a way possible, but let's stick to the instinctive solution that has came to us. So again, I must repeat myself. Maybe there is a way going downwards to identify a condition that this is the lowest common ancestor, but we are not going to think more in that direction. Let's stick with our intuitive feeling. That is, if there was a way to traverse upwards, this question could have been quite straightforward. We just had to traverse upwards, and the first time we meet, we just stop. So yes, let's program in a certain way, in such a way that the traversing upwards is not something that is not possible, but it's very much possible. And we can do that using a set. I'll call that set as ancestor, or not a set, basically a map. So this ancestor is a map or a dictionary, and what it will store is child, parent, nodes. So for 4, the ancestor of 4 will be 1, ancestor of 7 will be 1, 8 will be 7, 2 will be 7, 14 will be 2, 8 will be 2, 24 will be 14. And once we have this dictionary, what we can do is, once we have the parent information, we can use this dictionary to traverse upwards. And once we can traverse upwards, it's quite straightforward. We just have to find the lowest common intersection in the path. So no matter how much I repeat myself, it will be going to get clear only if I show you on the editor and actually program it. So I'm going to shift to my editor and show you how to implement this. The idea is that we are going to use ancestor dictionary, which will store child key values and child key and parent values, and we will use this ancestor dictionary to traverse upwards, not downwards. This is new, and once we can traverse upwards, it's going to be quite straightforward, as we will look, as we will watch. So let's shift to our editor. So let's begin programming. First of all, I'll declare ancestor as a dictionary with initial element as the root.data, that is root, and the child parent. Remember, this is child parent relation, so the parent of root is none, of course, makes sense. And then I'm going to basically perform a breadth first search on the tree. So q with element root, while the length of q is not equal to 0, I want to pop from q. So node is equal to q dot pop 0, popping from the front of the queue. If node dot left, that is if there is a left child, what I want to do is I want to append that left child to the queue, and I'll add this line. This is about adding ancestor data. So what I am doing is the ancestor of left child, and of course I'm dealing in terms of data here. So the ancestor of left child is the node dot data. That is, the node we are at is the ancestor of the parent of the left child. And again, for the right child, I'll be doing the same. Ancestor of the right child dot data is the current node dot data. So basically, it's not the ancestor. It should have been parent, but let's stick with ancestor. It's basically child-parent relationship. And this condition is to, if an1 is not in ancestor or an2 is not in ancestor, return -1. That is, there is no lowest common ancestor. Forget about lowest common ancestor. There is no ancestor at all. That means. Now I'll define S as a set. S will contain all ancestors of n1. I'll repeat, S is a set that will contain all the ancestors of n1, including n1. Okay, so let's do that. While I in ancestor, S dot add ancestor I. Now I'm doing the entire ancestor is in value. You could have done it in the terms of node, but I used values because it's just gonna make sense because we have unique values. We could have instead of inserting the values, we could have inserted the nodes in the dictionary, that ancestor dictionary. Now I have added the ancestor to S, and now I is equal to ancestor I. So I is the traversing element here. So now I becomes the ancestor of I, that is the parent of I. We are actually in this while loop traversing upwards, if you haven't realized yet. Other than that, we have then I is equal to n2. Now I'm going to use the same logic using the while, and this time I is equal to n2 to traverse upwards, not starting from n-word node but from n2 node. And if I find any element while traversing upwards in S, that is S that contains the ancestors of n1, I'll simply return and stop. So before starting the loop, if n2 in S, simply return n2 because that is the ancestor, common ancestor itself. Otherwise, we will be traversing upwards inside this while loop. If ancestor I in S, return node ancestor I. That is, we have found the lowest common ancestor. Otherwise, we will traverse upwards using the I element. So I is equal to ancestor I becomes the ancestor of I. And again, in the while loop, it goes on. Let's run and check if there is any error or typo. No, there's not. So let's submit and check if we can pass all the test cases. And yes, we can. So I hope with the actual coding, everything is much more clearer now. And the idea was that we created child father keys in the ancestor dictionary, and then we used that dictionary to traverse upwards starting from node n1 and stored all the ancestors in a set called S. Then iterating over the ancestors of n2 from most recent to oldest, father, grandfather, great grandfather, like that from for n2. We kept checking if there is the element present, the node value present in S. And mind you, S will contain all the ancestors of n1. And the moment there is one a presence found, we simply return the value and return that. So that we end there. So that was the entire logic, and that was the entire program. And with that, we have solved this problem.